This is the economics admissions assessment from November 2021. A few things to say before I start this. Firstly, this paper has been discontinued. This is the last paper that they'll publish. If you're asked to sit this paper, or if you were in a position where you would have been asked to sit this, you'll be asked to sit the Tamura instead from 2022 onwards. But this question is quite nice. This paper is quite nice because it's quite similar. It comes in two parts. Section 1 is what I'll be doing. It's part A is normal maths questions for 20 of them. Part B is advanced maths. This is the only bit that I'll be doing just because this is a bit boring. Section 2 was a economics essay question, so I'm obviously not doing that. I have no idea how you're supposed to do both of these parts in 60 minutes. I think a really good mathematician could do this part in 60 minutes, and I think a really good mathematician could do this part in 60 minutes. I have no idea how you could possibly expect it to be doing both in that time. Bit confused about that. I'm even more confused about how no mark scheme, work solutions or answer key has ever been published for this paper, despite it being almost a year ago. Super confused as to how no one thought that was their job to publish that. So while I've tried my best on this paper, I have no idea whether I've got any of this right. So let's just go for it. This is now the semi-official mark scheme for this paper because it's apparently the only thing that's ever been discussed about it. Anyway, for this first question, I just expanded out. 2 times 2 is 4, root x times root x is 4x. You do the same with this one to get this. 2 negatives make a positive. And then the cross terms cancel out to make 1s, and then there's minus 2 of them. So that's that. You differentiate it once you've put it into kind of power form. Differentiate it, this becomes a 4, that goes away. Negative comes down here, down to a minus 2. Then you just put in a half. Half to the power minus 2, well that's, the negative flips it over. Half flipped over is 2, squared is 4, times a quarter is 1, so it's 4 minus 1, which is 3. Good. Question number 22, I guess, or the second one I'm doing. Radius circle 2. Now hexagons are really nice because they create equilateral triangles inside of them. So for example, here's one of them, and then you've got a second one here, third, fourth, fifth, and sixth. And of course 360 degrees divided by 6 gives you 60 degrees, and because these two sides are the same, that gives you equilateral triangles here. So they're just made up of 6 equilateral triangles, which is very helpful. Because if this is 2 and this is 60 degrees, then we can say that's 30 degrees. Then we can just do some SOHCAHTOA. So cos of 30 is 2 over x, adjacent over hypotenuse. Rearrange that, cos of 30 is root 3 over 2, so that becomes 4 over root 3. You can rationalize that by timesing by root 3 over root 3 if you want to, you get this. That's of course this side as well, and it's of course this side because it's an equilateral triangle. And of course for the area of the hexagon, all we have to do is do half AB sine C for each triangle and then times it all by 6. So half AB, so 6 triangles, half times A times B, so that's these two lengths here, times sine of 60. Sine of 60 is also root 3 over 2. 4 times 4 is 16, divided by 2 is 8, 3 times 3 is 9. But then these 3's become a 3 cancel to get you down to 3 here. You sort this out, it's not that bad. 8 divided by 2 is 4, times 6 is 24, divided by 3 is 8, so it's 8 root 3 in the end. Cool. Question number 23. So you've got an arithmetic sequence. So it starts A, then it goes A plus D, then A plus 2D, then A plus 3D, and so on. Hopefully you know this formula, which is the formula for summing up the first n terms of an arithmetic series, where this is the first term, this is the difference, this is the number of terms. So let's just substitute n plus 1 into here, and we get this. Let's substitute n minus 1 into here, and we get this. This is a little bit annoying. Let's simplify this as much as we can. So just be careful. It's this thing times this, plus this thing times this. So that's what I've done there. The 2's cancel, and then you can multiply to make an plus what a, and then again the 2's don't cancel here, but this makes n squared d over 2, and then nd over 2. This one here, a little bit more complicated, because this is actually a double bracket you have to expand essentially. This goes into each one like this, and then this is nice and simple, the 2's cancel and you get the same thing you did over here. But here this is a double bracket, right, because it's n minus 2 times n minus 1 times d over 2 is how I kind of reshuffled that. Then I expanded this out, then you can put the d in over 2, and eventually just be careful with the negatives. And of course you're doing this one, which is this, minus this. So okay, this minus this, so these two cancel. A minus minus a is 2a. These two cancel. Nd over 2 minus minus 3nd over 2 is 2nd, because you end up adding them together. And then of course you've just got this d left over, which you're taking away because it was this one minus this one. And then this isn't any of the answers, but you can factorize out a d from this part, and you end up with the answer of g, I think, in the end. Good. Question 24. I thought a lot about difference of two squares here, because this is essentially a difference of two squares on top, but I couldn't make it work in any reasonable way. So I thought just binomial expansion then. So this is 2 to the power 4 plus 4, because the binomial expansion goes 1, 4, 6, 4, 1. So I haven't really written that properly, but sure. and you have 3 copies of the 2 here, and then 1 of the root 3, and then 2 copies, and then 2 copies, and then 1, and then 3, and then 4. You sort this all out. Root 3, of course, squared is 3. Root 3 cubed is 3 root 3. Root 3 to the 4 is 9. You get all this. The other one is basically the same, except the only difference is, you can treat this as just a plus minus root 3. So every time you take an odd number of root 3's, this changes to a minus, and every time you take an even number, it doesn't matter, because if you take 2 negative root 3's and times them together, you just get a positive number in the end. So I'm only changed the sign on things where I've got an odd number of root 3's. Sort this all out and you get this, which is very similar to this. When you do this, take away this, the 16's cancel, get 64 root 3 here, these cancel, 48 root 3 here, these cancel. And then all I need to do is, that's this time plus this time, is this, take away this. And then all I need to do is divide by 8. As I said, this divided by 8 is 8, this is 6, I think. Add them together to get 14 root 3. Cool. Question number 25. So if this thing squared equals 1, then that means that either this thing is 1, because 1 times 1 is 1, or this thing here is negative 1, because negative 1 times negative 1 is also 1. So we've got our 2 options here. Just solve either one. So take away 1 from both sides here. Now I don't need to know what the roots are, I just need to know how many there are. So I can very quickly check that b squared minus 4ac gives me 2 solutions there, because it's bigger than 0. 16 minus 8 is bigger than 0. That's 2 solutions, don't care what they are. Add 1 to both sides here. This very obviously factorizes to this, and so there's 1 solution here at x is minus 2. So we're going to have 3 solutions in total to this. Good. The polynomial, that is a factor of that. So I think the intention here is to make you do polynomial division. For long-time fans of my channel, you know that I'm not going to do polynomial division because I hate it. So all I'm going to do is set up that this original polynomial times this thing that they're calling a factor is equal to this thing times this thing here. Now I know this is a linear term because it makes a cubic in the end. So this is all that the first line is saying, right? That this thing times by something else is this thing. That's what a factor is. But now I can just compare, right? If I expand this out, I could very easily see that I'm just going to get an ax cubed. So a must be equal to p when I compare the 2 sides. And likewise, minus 1 times b must be equal to minus 1. So b must equal to positive 1. So I can just quickly sort that out, change the a out for a p because I know that's what it is. And now if I just expand this all out, I can do some more comparing. That should be a cubed, apologies, that should be a cubed. Sure, in fact I'll probably just quickly go in and change it, why not, just to make me feel better. So yeah, that should be a cube, let's go back to it. So we can see here again, there are no x's on this side, so minus x plus px must cancel out, so p must be 1. And likewise, there are qx squareds over here. So 1x squared minus px squared must equal q, but we know p is 1, so therefore q must be 0, and that's what the question was asking me. Apologies for the mistake in there. Question number 27. So we've got a circle, radius 2 centered at the origin, so I'll draw it. Sketching things is super important, in case you haven't noticed. X equals 1 is a vertical line down here. So that's the line x equals 1. Let's find the intersections between x equals 1 and the circle. So just put x equals 1 into here. 1 squared plus y squared equals 4. Take away 1 gets you y squared equals 3. So y is plus minus root 3. So this coordinate we'll say is 1 root 3, and this one would be 1 minus root 3. But of course now I can draw some nice triangles in here, which have a distance of 1 across, because of course you're going to the line x equals 1. A distance of root 3 up, and doing a quick little bit of Pythagoras. Actually, no, not even doing Pythagoras. This is just the radius of the circle, isn't it? So we get this here. And that's nice. And what I'll do is say, well, this is 60 degrees, because if I recognize trig values, I know that, for example, tan of 60 is root 3 over 1, or you could also recognize that cos of 60 is 1/2. So I can recognize this must be 60 degrees from exact values. And now what I can do is I can say, well, to work out this segment, what I'll do is I'll do this sector, take away this triangle. Right? So in pictures, it looks like this. So to work out this segment here, which is what they want, it's the whole this segment, it's the sector, take away the triangle. So that's my idea. So this sector here, it's pi times r squared times 120 over 360. That's a third, that's 4, so it's 4/3 pi. This here is a half times 2 times 2 times sine 120. Sine of 120, if you draw the sine graph, must be the same as sine of 60. Yeah, because it's 30 degrees back from 90 and forward from 90. Sine is symmetrical around 90. So this must be root 3 over 2. These cancel, so you get 2 times root 3 over 2, which is of course root 3. So it's this minus this, which is this one here, h. Good. Question number 28. So quadratic function, this has remained at this. So it's quadratic, so it looks a bit like this. That's the function. Now, I don't know how many people will have seen remainder theorem. I can never remember whether it's actually in A-level maths or not. Certainly not in year 12, I don't think. But factor theorem you will have seen. Factor theorem says if x minus a is a factor, then f of a equals 0. Now, two things to say. Firstly, this works both ways. So you could have said if f of a is 0, then this is a factor. But I just want to reword this slightly, because factor, what does factor mean? Well, it means something that divides with the remainder 0. Like 2 is a factor of 8, because 8 divided by 2 has no remainder. So what I'll say is x minus a divides with remainder 0, then f of a is 0. And this extends to remainder theorem, which says if x minus a divides with remainder n, then f of a is n. So you just replace the 0 with whatever number you want, and essentially the theorem just still holds. So what they're saying here is, because that's a minus 1 there, that means f of 1 is equal to 3. That's what remainder theorem says there. And this one here says f of minus 3 equals 5. So of course I can substitute both those things into here and say, well, f of 1 is 3, so I'll replace that with a 3 and put 1 in as the x's, which of course just gives me that, and then replace the f of x with a 5 and put minus 3's in here, which gives me that. And now lastly, one solution to this is x equals 2. So that of course means that f of 2 equals 0. And then of course I can just put 2 into here and say that equals 0. And you might not have seen a three-dimensional simultaneous equation before, but here's how you solve them. This one isn't too bad. Just take two different pairs. So I'll take this one and this one first, and I'll do this one take away this one. So 5 take away 3 is 2, this is 8a, this is minus 4b, and this is the c's go away, of course. All right, so that's this one take away this one. Next, take any other pair, so I'll take this one and this one, and do, again, just this take away this. 5 minus 0 is 0, is 5. This is 5a, this is minus 5b, and the c's cancel. And now I'm left with a two-dimensional equation, which I can definitely solve. So I don't even remember what I chose to do here. Okay, so I times this by 5, I guess, and times this one by 8. Take them away, and then divide by 20 to get b is minus 3 over 2. And, I was looking for the coefficient of x in f of x, which is b. And so I got it, minus 3 over 2. Good. Question 29. So to work out the mean of three numbers, you add them up and divide by 3. Very complicated. Now, of course, we know the log law that says we could multiply these three numbers together because the logs are adding. Obviously, that's a horrible idea. Don't do that. Notice that all of these are nice powers. This is 3 cubed. This is this is 2 to the 6, I believe. And this is 6 cubed. That's a harder one to spot. Bring the powers down to the front because that's what log laws tell you you're allowed to do. And now what I can say here is, okay, well, this is kind of interesting. You can do a little bit of tinkering here. They want the answer. I can't really just times these together because all these numbers are different. So what I'll do is I'll factorize out a 3, and then that 3 cancels nicely with that 3. I still can't bring the logs together because of this 2. So why don't we just put that 2 back? Say that's a 4, and now I can finally do 3 times 4 times 6 is 12 times 6, which is 72. And I think that will be the answer. Yeah, interesting. Question number 30. So this line meets this curve. I remember doing this question, and I did it in a really dumb way. I also don't know whether there's a better way of doing it, but I can guarantee that we have not done the same thing here, I don't think, if you have done this question. I think I've got it right, though. What I said was, okay, well, we're talking about meeting points. Let's set this one equal to this one, and look for the x-coordinate they meet. Rearrange that, times it all by 8, I think I did at some point. Yeah, that looks good. And then what I said was, okay, well, let's solve this. Well, I can just use the quadratic formula for that, right? Minus b is just 4, b squared is 16, plus 4 times 8 times c. Okay, so that's that. So that's my x solutions. And if I put them back into here, I can find my y solutions. So my y solutions are just half of each of those plus c. And of course, these two to come together, they make 4. So, and I can say, well, the solution is either with the plus or with the minus. So those are my two y coordinates of intersection. Finding the x-coordinates, then subbing them in to find the y. Okay, what can I do now? Well, okay, this simplifies a bit, right? Because you can just break this here and say this is 4 over 4 plus this over 4. But of course, 4 over 4 is 1. Ignore this for now. And then likewise here, this is 4 over 4 minus this over 4. That's just 1. And now saying the midpoint has y-coordinate 5. So if I add these up and divide by 2, I get 5. And that's what this is. If I add up this y-coordinate and this one, divide by 2, find the average of the two y-coordinates, I get 5. But something nice happens here, right? Which is that all of this horrible root and this one just cancel. 1 plus 1 is 2, c plus c is 2c. So you end up with 2 plus 2c equals, and I think, everything by 2 to make 10. And of course this solves for c as 4. And I think that's the answer. A crazy method. it's probably wrong as well, since I don't have that answer seems to sketch. Which of the following is the largest? First thing you do is sketch the sine and cos graphs. That one's the cos, this one's the sine. Okay, so what we can easily see here is that cos of 0.5 is bigger than cos of 0.75 or cos of 1. So let's eliminate them. And down here, likewise, we can see that sine of 0.5 is smaller than sine of 0.75, which is again smaller than sine of 1. So we're down to these two, and we just have to decide what's bigger, sine of 1 or cos of 0.5. Now, how do you work that out? Well, I used this rule here. Cos of pi over 2 minus x is the same as sine of x. This is, if you're more used to seeing this rule in degrees, cos of 90 minus x is the same as sine of x, and vice versa. I could have written the sine and the cos on the other side. Now, how am I going to use this? Well, if I just set x to be 1, and then say pi is like 3.14, so pi over 2 is about 1.56 going full engineer mode, and that's about equal to sine 1, but of course that's cos of 0.56 is about the same as sine of 1. Now, so that means I know sine of 1 is almost the same as sine of cos of 0.56, but cos of 0.56 is slightly smaller than cos of 0.5. So this one must be the biggest one here out of these two, and that'll be my answer. Number 32. There's lots of interesting things you could do here. On automatic, I just change these into the nice forms for circles. So completing the square here gives you a -1, which you add to both sides to get a 20, and completing the square here gives you 2 lots of -1s, which you add to both sides to get a 5. So okay, I did that. And then I thought, okay, these are two circles, they only intersect at one point. Picture two circles in your head and try and figure out how they're going to only intersect once. Well, it becomes very clear when you sketch these. So this one has a center of -1, 0, so it's somewhere over here, radius of √20. This one has a center of 1, 1, which is up here, and has a smaller radius of only 5. So it looks something like this, and this is the single intersection point, right? So this is my sketch, and I'm looking for this coordinate and then add up the two values. Now what I can do here is I can say, well, it's clearly on this line. And what's the equation of this line? Well, the gradient here is 1 over 2. Is the distance y and x, so it's y equals a half x, and then you can see that this point must be a half because it's halfway in between 0 and 1, so yeah, just a half. Okay, so how does that help me? Well, you could substitute that thing back into one of these to find the intersection, or you could be much smarter than that and just realize, okay, well, oh, I rearranged apparently. Well, what's this distance from here to here? Well, it's the distance across is 2, the distance up is 1, as we said, so 2 squared plus 1 squared is 5. So this is √5, this distance here, which actually means my sketch is terrible, because this circle should go through this point, and you can verify that by putting the point in there. But this distance is also √5, right? Because this is the radius of the smaller circle, as we've said. And so the distance from here to here is the same as the distance from here to the point we want. And that's 2 across and 1 up. So another 2 across, 1 up gets us to 3, 2. And I think that's... and then, of course, add them together to get 5. Good. Question number 33. Quite a nice question here. So you've got a geometric sequence. So it starts A, you times it by some number r to get AR, then AR squared, then AR cubed, and so on. It's telling you that the sum to infinity, which is this formula here, is 8/5, A over 1 minus R. Now, just make a note here. R has to be between -1 and 1 for that to work, non-inclusive. So just make a mental note of that in your head, or just write it down. Sum to infinity of the even numbered terms is that. Now look at the even numbered terms. We've got AR to start with, then we'll have AR cubed, then we go to AR to the 5, and so on. But this is just another geometric sequence. Starting term AR, geometric ratio R squared, right, each time. So we'll just put those into our formula and say that's equal to 3/5. And this is a simultaneous equation. That's cross multiply to get these two things. And what's the easiest way of sorting this out? Well, I see a 5a there and a 5a there, so let's just put this thing straight into there and times it by r. This is an equation in r. I know I'm going to be good here, do some rearranging. Pray that this factorize. It does. Make a note here. This answer is r equals 1, which we said we weren't going to have, so that's not an answer. This is the answer, r equals 3/5. It's actually asking for a plus r, so let's put that back into whichever one we want. It's not going to really matter which. Okay, I did it in this. I think I times everything by 5 here, and then 8 times 3 is 24. That makes 16, so it's 16 over 25. Add those two things together, times this by, I guess, 5 over 5 to make 15 over 25. That makes 31 over 25, which I believe is one of the answers. Good. Question number 34. Quite a difficult question here if you're not very comfortable drawing mod graphs. I have a method for this, which is weird. But anyway, y equals k is just a horizontal line somewhere at k. Now, what does this look like? We're looking at intersections. So what does this look like? Well, you've got to think about what absolute values or what mods actually do. If x is less than 4, like if x is 2, this is just 4 minus 2, and the mod value doesn't do anything, it's still just 2. And if x is minus 3, then it's just 7, and this still doesn't do anything. So if x is less than 4, these things don't do anything. So you just end up with this equation. And I can plot this, right? This has roots at 0 and 4, and it's an upside down quadratic because you get a minus x squared term. So that looks a bit like this. But again, that's only when x is less than 4. So I want to ignore that part of the graph, right? I'm just going to say that's the graph up to there. And now what's this point? Well, clearly the root is at 0 and 4, so this turning point is halfway in between, so it's got x coordinate 2. Put 2 in there, 2 times 4 minus 2 is 2, 2 times 2 is 4. So that's the point 2, 4 is the turning point. Could have also completed the square or whatever to find that. Now, when x is greater than 4, you've got 4 minus 5, for instance, and this thing is a negative. And what absolute values do to negatives is they times by minus 1. So, for example, if you have negative 6 in an absolute value sign, you just times negative 6 by negative 1 to give 6, and you get the answer of 6. So when x is greater than 4, I can just replace these signs with just a multiplication with a minus 1. Right? Because I'll get a negative number in here, and the absolute value will just times that by minus 1 to make it positive. So this is just the graph if this case. Expand that out, and you end up with this. So again, solutions at 0 and 4, but this time it's a quadratic that's the right way up, so it looks a bit like this. But again, I only care about this when x is greater than 4, so I'll just discount all of that part of the graph, and I get something that looks a bit like that. And so this is the picture that I've gone with for this graph. And it says what values of k give me exactly 2 points of intersection. Right now I have 1 when k is like bigger than 4. But if I just move k down a little bit, when do I have 2 solutions? Well, there, when k is 4, I get 1 here and 1 here. And if I go down to here, when k is 0, I get 1 solution on the root and 1 here as well. If you go any further down, you only get 1 solution again. So 0 and 4 are the 2 solutions that we're going to get for that question. Yeah, good. Question number 35. So how many times, again, we're going to sketch this as we've sketched so many things before. The first thing I thought to do was here, just factorize out the minus to make it more comfortable. Yeah, that factorizes perfectly to x minus 4 squared, which is nice. So this is very easy for me to sketch. It's just a upside down quadratic with 2 roots at x equals 4. So it's one of these guys with a y-intercept of minus 16. So that's very easy for me to draw. Where at this one, well, if I factorize that, I get this. So again, it has this same double root at x equals 4. This time it's a cubic though, and it's a cubic that has a positive x cubed term. So it starts down here and ends up here. It has if we expanded this out, it would have a y-intercept of 32, positive 32. And it's also got another root here at minus 2. So this is my sketch here. So how many times do these meet? Well, it's tempting to say 1, but always think cubics grow faster than quadratics. So my drawing's not very good, but this curve here is going to come down faster than this curve here is going to. So somewhere down here they will intersect, and GeoGebra will confirm that because this curve comes down much faster than this curve here, so that somewhere there will be intersection down here. And because just that's how quadratics work against cubics. And likewise, quartics would increase and decrease even faster. So the same kind of thing would happen. So there are 2 solutions, just here and down here as well. Excellent. 35 is an interesting question. I think hopefully if you've done lots of practice of this, as soon as you look at this, you think, okay, it's something to do with a quadratic. Okay, this is 3 to the 1 times 3 to the x, because if we add up the 1 and the x, we get x plus 1 up there. So I've split that apart. With a minus, that's of course 1 over. But of course, if you times everything by 3 to the x, you can cancel it out down here. You get another 1 in this term, and then of course you get 1 there. And now what I'm going to do is I'm going to replace 3 to the x with z. And now clearly this first time is 3 times z, which is 3z squared. This is plus 1, and this is kz. So this is clearly a quadratic if I rearrange it. And it wants me to have at least 1 real root. So it's very tempting to look at this and go, okay, all I need to happen is for b squared minus 4ac to be greater or equal to 0. That gives me at least 1 root. So okay, let's do that. B squared is k squared, minus 4 times 3 is 12. C is just 1, so cool. Okay, so that means bring the 12 over. Just be very careful. That means not only can k be bigger than root 12, which is just 2 root 3 essentially, but it can also be less than the minus of that. Because like think about an easier example, k squared minus 25 is bigger than 0. You can use minus 6, because minus 6 would square to make 36, and then you'd have something bigger. So you can be either side of this. There is a problem here, which is I wasn't just looking though for this to have or at least one solution, because let's say that this quadratic had 2 negative solutions, which is completely allowed here based on this working. If you put those negative solutions in for z, 3 to the x can't be negative. So for x to actually have solutions, I need z to be positive. Like I need the solutions to this to be positive. If I've got 2 of them, I just need one of them to be positive, because that'll give me one good x value, which is all I need. So, okay, how do we guarantee that the roots of this are positive? It's not just this. This guarantees that there are 1 or 2 roots. How do I guarantee that at least one of those roots is positive? Well, for the millionth time in this video, let's consider a sketch. Now, we know this quadratic goes through 1. That's the y-intercept. And it's a quadratic, right? So it either does this or it does this. So notice the fact that the y-intercept is positive means that it either has 2 negative roots or 2 positive roots, or 1 root if it just taps it either side, or no roots if it doesn't go down far enough, right? But the important thing here is it can't have 1 negative and 1 positive if you have a y-intercept of this. It has to have a negative y-intercept to have 1 negative and 1 positive root. So okay, all I need to discount, because I've already guaranteed with this rule here that I have at least one solution, all I need to discount is this type here, right? All I need to discount is the fact that I don't want it to be over here. How do I guarantee that? Well, notice the turning points, right? If the turning point is over here, where x is positive, then I'm fine, right? If the turning point is somewhere negative, then I'm not fine. So I just need a positive turning point. I need the turning point to be on the right somewhere. So okay, let's complete the square on this. So take a 3 out, halve this number. For a k over 6, take away the square, but all of this looks complicated. I don't need any of it. All I need is for this to be a translation this way, which just means I need k over 6 to be a positive number, which of course means I need k to be a positive number, which means cross-referencing that with this, I just need k to be that. This doesn't work because that gives me k as a negative number, which would move the turning point onto this side. So k, I just need to be this here. Cool. Question 37 is a question that is only for the brave, I think. What I thought was, okay, let's just factorize out that 3 straight away. And now, I think, yeah, I think this is the best way of doing it. You need to be brave enough to just rationalize, or try to, every single one of these terms. So times this one by root 27 minus root 21 over that, this one by this over that, and so on all the way down. Now what happens when you do this is, because this times this is 27, this times this cancels with this times this because of the negative. That's what rationalizing does. This times this is minus root 21. Sorry, minus 21. But likewise, because the difference on all of these denominators between all the numbers is 6, this one ends up being 27 minus 21 when you rationalize. This one ends up being 24 minus 18. This one 21 minus 15. This one 9 minus 3. You get denominators of 6 every single time, which of course means you can just put them all into one thing. Right? And now let's just think this through. We've got a root 27 here and a root 24 here. The next one is root 21. So notice how this root 21 cancels with this one, because you had a negative here. It's a positive there, but because I rationalized it, I times it by a negative. So it's a negative here, and then it's a positive later on when it becomes the first term. It will be the first one from this next one. Of course, the root 18 will do the same thing. I'll have a negative root 18 here, but then 2 terms along, I'll have a positive root 18, the one after this, which will be at the front. And that will go on all the way along. There's nothing to cancel with the root 27, and there's nothing to cancel with the root 24, because the highest negative you're going to have is this root 21 that comes from rationalizing here. So minus 21 is the first thing to cancel, and then it will cancel all the way down. Well, how far along can you cancel things? Well, nothing will cancel with this root 3 here, right? Because the one before this is going to be root 12 minus root 6. So nothing cancels with the root 3, but also nothing cancels with the root 6, because just like your 2 terms along here before you get to the start cancelling, you'll be 2 terms up from the top as well. Because essentially, there will be a root 6 at the end here, which will be a negative root 6 when you rationalize. But this next one would be the root 6 plus root 0, I guess, but it doesn't exist. So nothing cancels with root 6, nothing cancels with root 3, nothing cancels with these two either. This is 3 root 3, this is, I guess, root 4 root 6, which is 2 root 6. And then, of course, we can just start tidying this up. 3 over 6 is a half. Halve that. Is that any of the answers? No, okay, so this is root 2 root 3. Factorize out the root 3. And then halve this, and you get this here. And I think that's correct. Quite an interesting question. Good, we've only got a few questions left, which is excellent, because this is quite long. I'm going to say it straight up. This is the one question that I really wanted a mark scheme for, because I'm not sure whether I'm allowed to do any of the things that I've done here. I just did the obvious thing. I integrated this, right? I put in the limits, okay? I tidied up. I said, okay, well, this thing here is the integral. That apparently needs to be bigger than sine. The sines cancel. This I can write as 1 minus cos squared. And then I can put those together for this. And now I have a quadratic. Okay, great. I know how to solve quadratic inequalities. I factorize it. And what this means is either this thing, like I've got two things multiplying to make something bigger than 0. So either both of the things that are multiplying are bigger than 0, or both of the things that are multiplying are less than 0. Right? That's the only way to be bigger than 0 when you're multiplying two things, either both positive or both negative. Right? But now look at this case here. When we add 1 to both sides, we have cos of theta is bigger than 1. That never happens. Cos of theta is sometimes 1, but it's never bigger than 1. So that's just never a thing that will happen. So what I actually need is I need them both to be negative. And that's what I'll deal with here. Of course, this is easy to solve. Add 1 to both sides. This is fine, as cos is always less than 1 unless you're at 0 or 2 pi. Like it's every other time cos is less than 1 somewhere. It's always less than 1 unless you've got cos of 0, which is 1, and cos of 2 pi, which is also 1. So that's just basically always true. Now this one here, we need cos of theta to be less than this. Draw the cos graph. We want to be less than 0.5. Or we know that cos of pi over 3 is a half, 60 degrees, if you're still working in degrees. So of course, that's, and we know that this root here is pi over 2, because it goes 0, pi over 2, pi, 3 pi over 2, 2 pi. So that's pi over 2. So we're a sixth pi back to get to 0.5. So we need to go a sixth of pi forward to get to this bit here. So we do pi over 2 plus pi over 6, and that's 2 pi over 3. And that's that bit. Exactly the same over here. This is 3 pi over 2. Take away a sixth pi to get back to this root, and you'll get that. And so to be less than this, cos needs to be between these two values, which is this condition here. Again, that doesn't affect any of this, which is good. I'm not 100% sure that I'm allowed to do that, just that whole integrating, because I'm a bit concerned about what happens if this area is actually negative and it messes up. But I tried quite a few values of theta, and this does seem to be the range that works, I think. So I'm not 100% sure about that one, but I think it was the toughest question on here. But I don't know. Anyway, this point here is the point x, root x, we'll just call it, because this is just y is root x, so if this is x, this is root x. Now this is 15, so this distance I can say is 15 minus x, right? That's this distance from P to Q. Now this distance is clearly just root x, because that's what this means. And now the area of this rectangle, obviously, is 15 minus x times root x. And the question is, can I maximize that? So of course I'll expand out. I'll differentiate, which will give me this, if I just differentiate carefully. And then I want to make that 0, right? Like to find a stationary point, I want the derivative to be 0. Now this looks complicated, but if I just times everything by x to the half, I'll cancel it with this, and this will become an x to the 1. I'll just double everything, I'll add 3x, and I'll divide by 3, and I'll get x is 5. Substitute 5 back in, you get x is, you get this distance is 10, you get this distance is root 5, and the area is 10 root 5. Notice how 0 is also a solution here, but that's the minimum value. Like when you take x as 0, you get a minimal area here of 0, because it's just a line, not a rectangle. So that's the minimum. We found the maximum. You can differentiate this again for minus 3 over 2 to verify that's the maximum. Good. Okay, question number 40. I spent 5 minutes trawling through some Tamura papers because I am absolutely certain this was on one, but I can't find it. But I am certain this was on a Tamura paper. I think I just looked too fast and missed it. Okay, so let's add 1 to both sides. And now, of course, if the mod of all of this is 1, that means either all of this is minus 1, because modded, that's just 1, or, of course, all of this is just 1. Right, so we've got 2 branches to work with. Let's deal with this one first. Add 1 to both sides, we get this. Now, of course, if the mod of all of this is 0, that means that all of this is 0. That's the only number that becomes 0 when modded. Add 1 to both sides. And now, of course, if we have mod of this is equal to 1, either this is equal to minus 1, or this is just equal to 1. And that gives us 2 solutions. This one says the solution is at 2, and this one says the solution is at 0. Easy. Now we deal with this branch, add 1 to both sides. We know this is going to get a bit more complicated because of this 2. So either this whole thing is just 2, or this whole thing is minus 2 without the absolute value signs. Add 1 to both sides, we get this. Again, that means either this, well actually, look at this one. Mod of something cannot be negative 1 because the whole definition of this is that it will make it positive. So left hand side is positive, which can't equal a negative, so that's nothing. Add 1 to both sides here. That means that either this is minus 3 or it's positive 3. Solve both and you get 4 solutions in total. That's the whole paper. I hope that I didn't make too many mistakes, but you'll forgive me if I did. Again, no answer scheme, no answer key, no work solutions. I'm doing whoever job it is who works at Cambridge for them. I don't know why this didn't come with any answers. I'm pretty annoyed about it. This is supposed to be a proper paper. I'm calling you out hard, whoever works on that, because I know you watch the channel. But yeah, thank you for watching. I'll see you next time.